Hello students, welcome to the electrical engineering channel. In this lecture, I am going to start the section of synchronous motors. Synchronous motors are the second type of very important AC motors which also run on polyphase supply. So if a two-phase or a three-phase supply is given to the stator, the synchronous motors operate. The stator of the synchronous motors is very much similar to the stator of an induction motor, and it will require a polyphase supply so that a revolving magnetic field can be produced in the stator, and that revolving magnetic field will be linked with the rotor. But in synchronous motors, the rotor also requires a DC supply, and as a result of the DC supply or application of DC voltage, a constant magnetic field will be set up in the rotor, and that magnetic field will interact with the magnetic field of the stator so that the north pole of the stator will be attracting the south pole of the rotor. Similarly, the south pole of the rotor will be attracting the north pole of the rotor. South pole of the stator will be attracting the north pole of the rotor, and the synchronous speed will be the speed of the revolving magnetic field, and the stator magnetic field will be revolving as a result of the attraction of the stator magnetic field and the rotor magnetic field. The rotor will be locked with the stator magnetic field, and it will also rotate with the synchronous speed. So in synchronous motors, the speed of the rotor is exactly equal to the synchronous speed. So that's why these motors are called synchronous motors, because these motors run at synchronous speed. So when we apply a mechanical load at the output shaft of the synchronous motor, the speed of the rotor will remain same, but the rotor will be lagging behind the magnetic field of the stator by some angle alpha, and that angle is called as load angle. So when there is no load, the north pole of the stator will be exactly in front of the south pole of the rotor, and there will be no phase separation between these two magnetic fields. So the load angle alpha will be equal to 0. When we apply a light load, then the rotor will be lagging behind the stator magnetic field by some angle, where that angle is called alpha. And when we increase the load, that load angle will also increase slightly. But this load angle will be constant as long as the motor is running. So upon the application of a small load, that angle alpha will be, let's say, 20 degrees, and when we apply a slightly heavier load, then this angle load angle will become 40 degree, for example. But that angle will be constant at 40 degrees as long as the load is constant. So it means the motor will continue to run at the synchronous speed, or the rotor speed will be exactly equal to the synchronous speed, but the rotor will be lagging behind some angle which is called load angle alpha, and but the speed of the rotor will be constant, and it will be equal to the synchronous speed. So at no load, rotor is locked with the stator poles. As load increases, load rotor starts lagging behind the stator poles by angle alpha, but still runs at the synchronous speed. So this is the property of the synchronous motor, and there is no slip in synchronous motors as we have observed slip in the operation of induction motors. Now we will discuss the phenomena of back EMF in synchronous motors. In DC motors, we can observe back EMF in the stator. So back EMF is the EMF which is induced at the stator side due to the rotor magnetic field. So in DC motors, the expression for back EMF is given as N phi Z over 60 into P over A. Here N is the rotor RPM, phi is the flux, Z is the total number of conductors, P is the total number of poles, and A is the number of parallel paths. So this is the expression valid for the DC motors, and in DC motors, the armature current is equal to V minus EB over RA. A is the armature resistance, V is the applied voltage, and EB is the back EMF. Another very important phenomena which must be taken into account in AC and DC machines is that in DC machines, the field winding is done on the stator side and armature winding is done at the rotor core. But in synchronous machines, this these windings are opposite. So in AC machines, field winding is done on the rotor and armature winding is done at the stator. And stator core is also called the armature core. So here the winding which we do on the rotor is called field winding, and the current which actually flows through that rotor winding is called field current, and greater is the field current, greater will be the field excitation or the rotor excitation. So in synchronous motors, ZS is the stator impedance, and it is equal to the resistance of armature winding or armature resistance plus JXS. XS is the stator reactance, and IA is equal to V minus EB over ZS. And ZS is equal to the resistance and the reactance of the stator. In DC machines, we know that say this reactance is equal to zero when we apply a DC supply to any winding. The reactance will be equal to zero because reactance is equal to omega L, and for DC supply omega is equal to zero. So we will only have the armature resistance in DC motors. But in AC motors, we will have the armature resistance as well as the stator reactance. So V is equal to EB plus IAZS. And here in DC motors, the back EMF depends on the RPM. So greater is the speed of the rotor, greater will be the back EMF. But in AC motors, the back EMF depends on the excitation voltage, not on the speed. So excitation voltage is the voltage applied at the rotor side to produce the magnetic field. So greater is the applied voltage, greater will be the field current, greater will be the excitation voltage, and greater will be the back EMF. So under no load condition, this is the applied three-phase voltage which is applied at the stator, and opposite will be the back EMF. This is the induced EMF at the stator side due to the rotor. So these two EMFs are 180-degree out of phase with each other, and we can draw an analogy between the direction of these two voltage vectors by looking at these magnetic fields of the stator and the rotor. So if we observe this figure, we can see that the direction of magnetic field of the stator is opposite to the direction of magnetic field of the rotor. So the applied voltage corresponds to the applied three-phase voltage corresponds to the magnetic field at the stator side, and the back EMF corresponds to the the EMF due to the magnetic field of the rotor side. So since these two magnetic fields are opposite in nature, so the resultant EMFs will also be opposite with each other. So here we will see this analogy, and these two voltage vectors are exactly in opposite directions due to the opposite directions of magnetic field in of the stator and the rotor. But when we apply a slight load, there will be slight angular displacement between the stator magnetic axis and the rotor magnetic axis. So the direction of induced EMF at the stator side and the direction of the back EMF will also undergo a slight angular displacement. So as a result, when we apply a slight mechanical load at the rotor shaft, this back EMF voltage vector or back EMF vector will undergo slight displacement, and we will observe a small load angle alpha which can be seen in this phasor diagram. And this load angle is equal to zero when we apply no load at the rotor shaft. And this is the direction of back EMF. This is the direction of the applied voltage vector. And since the motor winding is inductive in nature, so the armature current will be lagging behind this applied voltage by angle phi. So this angle phi corresponds to the power factor of the stator winding. So this since the stator winding is inductive in nature, so there will be a lagging power factor of the motor. Now this ER is called the reactance voltage, and this is actually the voltage induced at the stator winding. So ER is equal to IAZS. So in this equation, V is equal to EB plus ER, and EB is the back EMF, and IAZS is the ER, which is called the reactance voltage. So this is the direction of ER, and this is the direction of the current, and current is this is equal to IA, and ER is equal to IAZS, and ER can also be written as IARA plus JIAXS. So this ER has further two components, IARA plus JIAXS. In synchronous motors, the armature resistance is very small, since the armature winding is made up of copper. So copper is a very good conductor, so the resistance of the copper winding is very small as compared to this reactance. So Ra can be ignored, and we can write IAZS as JIAXS. So this is IA. So the ER, which is approximately equal to JIAXS, will be at right angle to this IA vector. So the ER will be lying at almost 90 degrees with this armature current. So this is the direction of ER. But if we are not ignoring the armature resistance, then this ER vector will not be exactly 90 degrees with this armature current, but slightly smaller than 90 degrees, for example 80 degrees or 85 degrees. But if we ignore this RA, then ER will be exactly at 90 degrees with this IA vector. So I hope this thing is now very much understandable. Now this is the back EMF. So in order to uh, conclude this expression, which is saying that V is the vector sum of back EMF and the reactance voltage V is equal to EB plus ER. So we have to place this back EMF vector at the top of this applied voltage vector. So this is EB, and now we have to produce EB dash vector. So EB dash vector will be opposite to that EB vector, and this is EB dash vector, which is exactly parallel, or which is exactly anti-parallel with this EB vector, and this is EB dash vector. So the vector sum of this ER, so this is ER vector, this is EB dash vector. The vector sum of these two vectors is the applied voltage vector. So V is equal to ER plus EB. So by making these analogies, we can draw the complete phasor diagram of the quantities associated with the synchronous motors. Now we are moving towards the calculation of the powers associated with the synchronous motors. So here I have again drawn the phasor diagram of the synchronous motor. So this is the back EMF, this is the load angle, this is the applied voltage. So this is back EMF, so this is also back EMF, and this is the reactance voltage IAZS. Here we have IA, and this is IA. The angle between IA and V is phi, and theta is the called the internal angle, and this theta angle corresponds to the angle between IA and ER. So this is the reactance voltage ER, and this is IA, and this is also IARA. Since RA is the real number, so IA will be in phase with IARA, and this is JIAXS. So the angle here which we see as theta is called the internal angle. And if we ignore RA, or if the winding is purely inductive, then the angle between IA and JIA axis will be exactly equal to 90 degrees. And now this input power is equal to under root 3 line voltage into line current into cos phi, and phi is the voltage between the applied voltage and the armature current. And the mechanical power can be written as the product of back EMF and the armature current multiplied by cos alpha minus phi. So mechanical power is equal to back EMF multiplied by armature current into cos of angle between them. Now the angle between EB and IA is alpha minus phi, which we can observe from this phasor diagram. This is EB. The opposite of EB will be lying over here, and this angle is phi between V and IA. Now if this angle is alpha, then this angle will also be equal to alpha. So this is the angle between V and EB, and here we have EB over here. This is V. So the total angle between EB and V will be alpha. So the angle between IA and EB will be equal to alpha minus phi. So we have to subtract this phi from this whole angle alpha, and then we will get this angle which is alpha minus phi. So this is the expression for the mechanical power, and it is equal to EVIA cos alpha minus phi, and the total input power is equal to the mechanical power plus the stator copper loss, and stator copper loss is equal to IA square RA, and mechanical power is equal to input power minus IA square RA, and mechanical power is equal to three-phase mechanical power is equal to this under root 3 VL IL cos phi minus 3 IA square RA. So this power distribution can also be represented by this figure, and here we have input power which is divided into stator copper loss and the mechanical power, and the mechanical power is further divided into iron and the friction losses, iron losses which are also called core losses, and the friction losses which include windage losses. And after subtracting these losses from the mechanical power, we will get the output power. So this thing can also be explained by using this figure. Here we have the total input power. From this input power, if we subtract the stator copper losses, we will get the mechanical power, and from the mechanical power, if we subtract iron, friction, and windage losses, we will get the output power. So this is the equivalent circuit of synchronous motor. This is the stator side. This is the rotor side. Stator side is also called the armature side. Here we have armature current, armature resistance, and the stator reactance. So this is corresponding to the armature winding. And unlike the DC motors, we don't see any small circles over here. Those small circles actually correspond to the carbon brushes, but in synchronous motors or in induction motors, we don't use any carbon brushes at the stator side, so there are no circles present over here. This is the rotor side, and here we have the field winding. This is the DC voltage applied at the rotor, and here we have a current limiting variable resistor. So if we want to increase the excitation, we will reduce this resistance and vice versa. So this is again the phasor representation of the synchronous motor. Here we have the applied voltage. This is the armature current. This is the back EMF, and the angle between back EMF and the applied voltage is alpha, and the angle between V and IA is phi. So this is back EMF. This is IARA. IARA will be in parallel with IA, and JIA axis will be at 90 degrees with IARA, and the vector sum of these three vectors EB plus IARA plus JIA axis is the applied voltage vector. So V is equal to EB plus IARA plus JIA axis. So if we ignore this armature resistance RA, then this very small voltage drop will be ignored, and in that case V will be equal to EB plus JIA axis. So this will be the resultant figure if we don't consider RA. So RA is very small. So here we have the armature current vector, and we will have only EB vector and the IA axis vector. So in this case, this IA will be at 90 degrees with this IA axis vector. So the angle between IA and IA axis vector or JIA axis will be 90 degrees, and the angle between this V and EV is alpha. So now we have to calculate this vector AB, and this AB vector can be represented by two expressions. So first expression will be written in terms of this EB. So this EB will have two components. This is the horizontal component, and this will be the vertical component. Since its angle is alpha, so horizontal component will be EB cos alpha, and the vertical component will be EB sin alpha. So AB will be equal to the vertical component of EB. So AB is equal to EB sin alpha. Similarly, this AB can be represented in terms of this IA axis vector, and this is the IA axis vector, and we have this angle phi between V and IA. So the angle between AB and IA axis, so this angle will also be equal to phi, because the angle between two lines is same as the angle between their perpendiculars. Now this voltage vector is the perpendicular at of this AB vector, and the perpendicular of this IA vector is this IA axis vector. So the angle between this voltage vector and IA vector will be equal to the angle between this IA axis vector and the this AB vector. So this angle is phi. So now we have to calculate two components of this IA axis vector, assuming that phi is the angle between IA axis and AB. So this vector will be IA axis sine phi, and this vector will be IA axis cos phi. So AB will be equal to EB sine alpha, and it will also be equal to IA axis cos phi, because the component in front of the angle is always vertical component, and the angle at and the component with the angle is always called the horizontal component. So this component will be IA axis cos phi. So RA is very small and we have ignored it. So this EB sin alpha is equal to IA axis cos phi. So it will become EB divided by XS sin alpha equal to IA into cos phi. Now we can multiply both sides with voltage. So VEB over XS sin alpha is equal to VIA cos phi. So VIA cos phi is equal to EBV over XS sin alpha. So this is the per phase input power P in. So it means this is also per phase input power. And for the calculating the three phase power, we will multiply this expression with 3, and P in is equal to 3 EBV over X sine alpha. So since we have ignored RA in deriving this expression, so stator copper loss will be equal to 0. So mechanical power will be equal to the input power in this case. So mechanical power is equal to 3 EBV over X sine alpha. So that is all about our today's discussion on synchronous motors. I hope you have understood the basic principle and basic phasor diagrams of synchronous motors. For watching more similar videos, please stay tuned to this channel. Until the next lecture, it's goodbye.